Hello everyone, welcome back to another video. My name is Johnny Vu, and we'll be discussing reinforced learning. This is week 6. So today I will be trying to provide you a solid understanding of what reinforcement learning is, how it works, and where it is currently being applied, especially in cutting-edge applications like training sophisticated language models. We'll also discuss the future trends and potential directions this exciting field is heading. Okay, so what is reinforced learning? Reinforced learning is a type of machine learning where an agent learns to make sequential decisions by interacting with an environment. The primary objective is to maximize the cumulative reward received over time. Unlike other forms of machine learning, such as supervised learning, RL does not rely on labeled data. Instead, the agent learns through a process of trial and error, discovering which actions yield the most favorable outcomes. This learning is achieved by receiving feedback in the form of rewards or penalties, which guide the agent in refining its decision-making progress. To make it easier to think about, we could think of this as like a dog. When the dog performs a desired action, such as sitting on command, you reward it with a treat. Conversely, when the dog engages in undesirable behavior, like chewing on furniture, you might you might issue a verbal correction. Over time, the dog learns to associate its actions with these outcomes, gradually adjusting its behavior to maximize rewards and avoiding penalties. This simple yet effective feedback loop is the essence of reinforced learning. Some of the key components to consider when it comes to reinforced learning are agents, environments, states, action, rewards, and policies. The agent is a learner and a decision maker. It perceives its environment, takes actions, and learns from the consequences of those actions. The environment is the world in which the agent interacts. It responds to the agent's actions by transitioning to new states or and providing a reward or penalty. A state represents a specific situation in which the agent finds itself. It includes all the information available to the agent that might be relevant for making the right decisions. An action is a move or decision made by the agent. The choice of action influences the subsequent state of the environment and the rewards perceived. The reward is the feedback signal from the environment and that evaluates the agent's action. A positive reward encourages the agent to repeat an action, while a negative reward or a penalty discourages it. A policy is the strategy used by the agents to determine which action to take in the given state. It map it that it maps states to to actions, guiding the agent's behavior. An example we can see is AI in the form of ping pong. The state that would include the ball's position and reward. The state would include the ball's position and the positions of both paddles. The action would be to move the paddle up and down. The reward would be positive for hitting the ball and negative for missing it. Through repeated play, the AI learns to position its paddle effectively, maximizing its score by consistently hitting the ball. So how does reinforced learning work? The first step in the reinforced learning process is to define a policy which serves as the agent's strategy for making decisions. This policy takes the current state of the world as its input and outputs the action that the agent should take. For example, in a game like ping pong, the inputs to policy might be the x and y positions of the ball, whether as well as the positions of the two paddles. Based on this information, the policy determines whether the agent should move its paddle up or down. In many in many modern reinforced learning applications, the policy is represented as a neural network. This allows the agent to learn complex and nonlinear relationships between states and actions. The neural network takes the input values, multiplies each value by its weight, and sums them up to the product as a result. To convert this result into a greater value between 0 and 1, a sigmoid function is often applied. If the resulting value is greater than zero point 0.5, the agent might move up, otherwise it moves down. The neural network effectively learns to map states to actions through adjusting its weights during the learning process. Initially, the agent can be trained using supervised learning techniques. This involves using a coach to guide the agent's actions at every step. The coach provides the correct action for each state, allowing the agent to learn the optimal behavior. During this phase, an error function is defined to measure the difference between the agent's actions and the coach's guidance. The agent then optimizes its weights to reduce this error, effectively mimicking the coach's behavior. Once the agent has undergone initial training, reinforcement learning is used to refine this policy. In this phase, the agent learns from its own experiences, receiving rewards, penalties for its actions. If the agent loses a game, all the actions it made during the game are penalized. Conversely, if the agent wins, all its actions are rewarded. To account for the varying importance of actions throughout the game, later actions are often penalized or rewarded more heavily, as the outcome of the game typically depends more on the final moves. This process encourages the agent to learn which actions lead to favorable outcomes and to adjust its policy accordingly. To encourage exploration and prevent the agent from getting stuck in suboptimal solutions, probabilistic policies are often employed. Instead of making deterministic decisions, the agent assigns probabilities to different actions. For example, the probability of 0.7 means that there's a 70% chance of moving up and a 30% chance of moving down. This randomness allows the agent to explore a wider range of strategies, potentially discovering better solutions that it might have missed with a deterministic policy. The randomness helps the agent escape a local minima where it might otherwise remain trapped. One of the fundamental challenges in reinforced learning is balancing exploration and exploitation. Exploration involves trying new and potentially risky actions to discover new strategies and gain better understanding of the environment. Exploitation, on the other hand, involves using the knowledge and strategies that the agent has already learned to maximize its rewards. Finding the right balance between these two is crucial for effective learning. Too much exploration can lead to wasted time and missed opportunities, while too much exploitation can prevent the agent from discovering better solutions. Another significant challenge is the risk of getting stuck in a local minima. Local minima are suboptimal solutions where the agent's performance is relatively good but not the best possible. Once the agent reaches a local minima, it can be very difficult to escape and discover the globally optimal solution. To address this, various techniques are used, such as introducing randomness into the policy to encourage exploration of different strategies. By occasionally taking the suboptimal actions, the agent can potentially break free from the local minima and discover a better path. The delay between an action and its corresponding reward can also pose a challenge. In many real-world scenarios, it may take a long sequence of actions to ultimately receive a reward. This makes it difficult for the agent to determine which specific actions were the most influential in achieving the reward. The agent must learn to assign credit to the appropriate actions, even when the reward is not immediately apparent. This requires sophisticated techniques such as temporal difference learning to propagate the reward signal backwards through time. In some domains, it can be difficult to evaluate the quality of different solutions. This is particularly true for creative tasks such as writing jokes, poems, or summaries. In these cases, there may not be a clear and objective metric for measuring success. Instead, subjective human judgment is often required. However, obtaining reliable and consistent human feedback can be challenging and expensive. This makes it difficult to train reinforced learning agents for tasks where human evaluation is essential. Reinforcement learning from human feedback. What is that? Reinforcement learning from human feedback is an innovative framework that integrates human feedback directly into the training process of a reinforced learning algorithm. This approach leverages human insights to guide and accelerate the learning process, enabling the algorithm to make more informed decisions and achieve better outcomes. The primary reason for incorporating human feedback is to address the limitations of traditional reinforced learning. In many complex tasks, it can be challenging to define a clear and objective reward function that accurately describes the desired behavior. Human feedback provides a valuable source of information for shaping the reward signal and guiding the algorithm towards a more human-aligned solution. Additionally, human feedback can help overcome issues such as reward sparsity, where the agent receives infrequent or delayed rewards. The process begins with human labelers who provide feedback on the model's outputs. This feedback can take various forms, such as ranking different responses, assigning scores, or providing textual evaluations. The goal is to capture human preferences and judgments regarding the quality and the appropriateness of the model's behavior. A separate neural network known as the reward model is then trained to predict human preferences or scores. This model learns to mimic human judgment, providing a continuous reward signal that can be used to guide the reinforced learning process. The reward model is trained on the data collected from human labelers, allowing it to generalize to new and unseen outputs. Finally, the main model is fine-tuned using the reinforced learning, with the reward model providing the reward signal. The goal is to optimize the model's policy to generate outputs that receive high scores from the reward model. This iterative process of feedback, prediction, and optimization allows the model to progressively improve its performance and align its behavior with human values. One good example of this in practice is the training of ChatGPT. In this case, human feedback is used to train the reward model that predicts the quality and helpfulness of different responses to a given prompt. Human labelers rank various responses, and the reward model learns to predict these rankings. ChatGPT is then optimized to generate responses that score highly according to the reward model, resulting in more coherent, informative, and engaging conversations. One of the most exciting trends in reinforced learning is the development of models that can handle multiple multidades of data, such as text, audio, and images. These multi-model reinforced learning models have the potential to revolutionize human-computer interactions and enable more natural and intuitive interfaces. The key to achieving multi-model learning is to represent different types of data in a common format, such as tokens. For example, audio and images can be tokenized and processed in the same way as text. This allows the reinforced learning model to seamlessly integrate information from various sources and make decisions based on a more comprehensive understanding of the environment. Another promising direction is the creation of reinforced learning agents that can perform tasks over extended periods. These long-running agents are capable of managing complex projects, coordinating multiple subtasks, and adapting to changing circumstances over time. However, developing long-running agents presents significant challenges, including the need for robust supervision and error correction mechanisms. As these agents become more autonomous, it's critical to ensure that they remain aligned with human values and goals. As reinforced learning models are applied to increasingly complex tasks, the need to process and reason about long context becomes paramount. Traditional reinforced learning techniques often struggle with long-range dependencies where the influence of past actions on future rewards is not immediately apparent. To address this, researchers are exploring new ideas for managing and leveraging long context effectively. This includes techniques for compressing information, focusing attention on relevant details, and maintaining a coherent representation of the task over extended periods. So from all of this, what can we conclude? Reinforced learning is a powerful and versatile technique for training AI agents to make intelligent decisions through interaction and feedback. By learning from their experience, reinforced learning agents can adapt to complex environments and achieve remarkable levels of performance. Reinforced learning from human feedback further enhances reinforced learning by incorporating human preferences and judgments, leading to improved results and better alignment with human values. Reinforced learning is the driving notation across a wide range of fields, from game playing and language modeling to robotics and autonomous systems. As the field continues to evolve, we can expect to see even more groundbreaking applications of reinforced learning in the years to come. Some things to take away from this presentation is that reinforced learning is not just a theoretical concept, it is a practical tool that is actively shaping the future of AI. By understanding the principles and applications of reinforced learning, you can gain valuable insights into the next generation of intelligent systems and their potential to transform our world. Thank you for watching.